Now, before we actually get into the content for today, I thought it might be good for me to establish some street credibility here. Because you're like, okay, Steve, you seem like a nice guy, but why should we trust you when it comes to Laplace transforms? Well, what are Laplace transforms named after? Who is it named after?
Mr. Laplace.
Yeah, Laplace, exactly. It's named after Pierre-Simon Laplace. Now, he had a student whose name was Michel Chalet. Now, he had a student, Hubert Newton, who had a student, Eliakim Moore, who again had a student, George Birkhoff, who had a student, Hassler Whitney. And you're probably wondering, where is this going? There was another student, Herbert Robbins, who taught Herbert Wilf. There was sort of the Herbert generation there, who taught somebody named Fan Chung, who taught me. So what you see is generation after generation, knowledge has been passed down from master to student. And so in other words, what you see here is every one of these was what they call a PhD advisor. Now, what you may not know is after you get your PhD, there's various ceremonies. They bring us into a candlelit room, and our advisor starts chanting, the Laplace transform of e to the ct is 1 over s minus c. And this goes on for hours. Knowledge passed down from one to the other. And now I pass it to you. So there you go. All right, so there's my street cred. Okay. Now, I was going to jump right into today's sort of new function, but there were a couple of things that I feel like I wanted to make sure I emphasized from last time. So I just want to do a quick few comments about unit step function, because this is it's a really nice function, actually. And as a reminder, what's happening, well, u of t minus a. So u of t, this is, it does what? It's 0, then it's 1, and it does this at the location a. So it's a jump. But really, this is our on-off type function. So turning things on and off. And you want to be comfortable with being able to transform both Laplace and inverse Laplace, what's going on. So there's the rules. The Laplace transform of u of t minus a, f of t minus a, is f of s e to the minus as. And where do people make mistakes? Well, one of the things is they often forget that whatever's attached to this unit step function, u of t minus a, has to look like t minus a on the inside. And if it doesn't, you're not ready to do it. It being take the Laplace transform. So there's this nice tip here that says, look, if you need to rewrite it in terms of t minus a, just remember t is t minus a plus a. And that oftentimes can be very helpful. And I think it's good to get into the habit of sort of saying, when I see certain things, I know what's coming. So for instance here, when I see this u of t minus a, I say, okay, that means in the transform, I'm going to have e to the minus as. So it's a connection I make. I know it's coming. And then in the back of my head, I say, well, whatever's attached, this f of t minus a, I say, well, mentally I say, what is f of t? And then that is what gives me my f of s. So it's nice to understand what's the contribution from the different parts. Now, of course, every rule for Laplace is a rule for inverse Laplace. So the inverse Laplace of f of s e to the minus as means that there was an on-off switch that occurred. And so whenever I see this e to the minus as, I know that there's going to be this on-off function coming into play, u of t minus a. And then I say, okay, same thing as before. I see this f of s, and first thing is I say, well, what is the corresponding f of t? And then I say, aha, remember to carry out the shift. So it's easy to forget carrying out the shift. So basically the rule of thumb is exponential functions they go together with shifts. And don't forget about the shifts. And I like to say, look, it can be useful to write down the effect. So it's like, oh, e to the minus as means shift by a. And then I can say, okay, that's good for me to remember. Now, why do we like unit step functions? Why are they so useful? Well, they're very useful for anything that's piecewise. So it's a great way to describe piecewise functions. And remember, what does that mean? Well, piecewise just says, I change my behavior. So my behavior changes from one point to another point. So how do we capture that? Well, what we say is that we're turning on and turning off our behavior. So that's what the step function does. It turns things on and off. So I want to turn off what was happening beforehand, so that's why I subtract. I want to turn on what needs to happen afterwards, so that's why I add. So the net effect is turning off what came before, turning on what comes after. And so if you have something written as a piecewise, or maybe if you have a picture, you can say, okay, let me just figure out what each part of it is, what the behavior of each part is, and then you can write it as a string of these put together. And there's this comment here. It says, look, we can solve differential equations involving piecewise functions. So when it says involving piecewise functions, what it's really drawing to is this right-hand side is piecewise. Okay, well, so here's an example. X double prime plus x prime is 1 plus 2 ut minus 2 with x of 0 equals 1 and x prime of 0 equals 0. Now, could we have solved this before? Yes. And if you watch all of the content, we actually did an example like this. What's the idea? Well, you just say, okay, let's solve it sort of before 2. So you have x double prime plus x prime equals 1. And you have your initial conditions that were given, and that holds up until you're turning something on and off. So that holds between 0 and 2. And now you say, well, look, I had initial conditions at 0. So initial conditions can now give me what I can call terminal conditions. So in other words, I can figure out what happens at 2. Well, the thing is, what I end at 2 for one part is the start at 2 for my next part. And so I have to feed that into my next part. So that's like, great, now I have a new differential equation to solve using new conditions. And then I have to figure that one out. So you actually have to solve it multiple times. And then you have to put it all together. So that's if you don't use Laplace transform. And if you do use Laplace transform, you just do it. It's built in. It captures everything. You don't have to think, oh, what do I do about this transition from one part to another? It's already taken care of. And that's why Laplace transform works so amazingly well with these piecewise functions. Because if it wasn't piecewise, what a headache. Oh my goodness. Oh my goodness. Okay, so that's some comments. One more comment. An example. Suppose I ask you to do the following. Find the inverse Laplace. Upstairs, 6s minus 9 e to the minus 2s. Downstairs is s minus 2 over s plus 1. That doesn't really seem like much of a comment, more like an example. But there's something that's going to happen here that I just want to emphasize. There's something I have seen many students do. So many points were lost that didn't need to be lost. And I just don't want I don't want you to lose any more points. I want you to get all the points. Okay, so when you approach this problem, what do you need to do? Okay, there's going to be some partial fraction going on. Good. All right. Great. So far, that's a good answer. Okay, so downstairs, of course, we have our s minus 2, s plus 1. Upstairs, we have our, I hesitate to do this because, okay, I'm not going to do it yet. 6s minus 9 e to the minus 2s. And we ask the question, are we ready to start partial fractions, and why not? Okay, so there's actually two questions I asked. The first question, are we ready to start partial fractions? No is the correct answer. Why not? Because I said so. Well, that's a good reason, but there should be a reason as well. What? There's somebody who wasn't just I said so. This exponential. Yes. You see this exponential thing? It turns out, true story, exponentials are not polynomials. Now you might say, well, that's a great story, Steve, but what does that have to do with partial fractions? So here's the comment. Partial fractions, and sorry, it's a very long comment, so it's going to take me, it's very dramatic. You're like, ooh, what's he going to say about partial fractions? Well, the thing is, it doesn't work for all types of functions. It only works for polynomial over polynomial. That's it. If you don't have polynomial over polynomial, it won't work. You can kind of mimic the process, but it will fail. And you'll get the wrong thing. Okay, so given that we have this statement, partial fractions only works for polynomial over polynomial, and that we have this exponential here, are we hopeless? Do we have to give this problem up? And the answer is no, we don't. What do we need to do? Separate it, yes. So what you have to do is you have to pull it apart. So we're going to pull it apart in the following way. 6s over s minus 2s plus 1. And then minus, I'll have 9 over s minus 2s plus 1. And I'm even going to pull this all the way out to the side, e to the minus 2s. This is the same function. It's just written in a different way. But now, what we have is we have these parts. Now, here is, of course, the somewhat, you might say, oh, that's disappointing. Or like, oh, I'm okay with that. We actually have to do partial fractions twice. One part for the piece without the exponential function attached to it. One part which should have the exponential function attached to it, which we put off to the side. So it's like double partial fractions. But that's okay because it means we get the right answer. And it turns out the right answer is worth more points. It's fun how that works. All right, should we finish? Yeah, of course we should. Well, in for a penny, in for a pound, as they say. So 6s over s minus 2, s plus 1. Well, our two denominators, s minus 2, s plus 1. What goes on top of the s minus 2? Yeah, just a. How about that s plus 1? B. We clear our denominators. We'll get 6s equals a times s plus 1 plus b times s minus 2. Okay, well, what do you want to do here? Make good choices. I like that. So we're going to make some good choices. Someone suggested apply s equals 2. We're going to get 12 equals 3a. What does that tell us about a? Equals 4. Okay, is there another good choice? -1. S equals -1. -6 equals -3b. What does that tell us about b? B is 2. All right, and then we have to repeat it again for this other part. So that's all right. The good news is we say, oh, it's very similar, so we at least have a good idea of what's coming. It's the same a over s minus 2 plus b over s plus 1, but of course here a and b are going to be different. We clear our denominators, similar as before. The only part that's really going to change is instead of 6s, we have 9. But of course, that will change our final answers. All right. Well, good choices worked once. Good choices should work again. Okay, so we make more good choices. It's actually the same good choices. Plug in 2. 9 equals 3a. So now, in this case, what is a? 3. Plug in negative 1. We get 9 equals minus 3b. So b is negative 3. So all our work gets us to the following point, namely that our problem is the Laplace inverse of, well, we'll start with this part. We have 4 over s minus 2, which we'll write as 4, 1 over s minus 2. Then plus b, so that's a 2, and I'll just write that in front, 1 over s plus 1. And subtract, throw in some parentheses there, because we always like our points. Here we have a over s minus 2, so that's 3 over s minus 2. And then we have b over s plus 1, which is a minus 3, 1 over s plus 1, and there's an e to the minus 2s. All right, so when I look at this and I think about how I'm going to figure out the answer, I work through the parts. And I say, okay, this 1 over s minus 2, just that by itself, what does that become? E to the 2t. 1 over s plus 1. E to the negative t. And it's actually this, I'm still going to write the same here. It's still e to the 2t. Here it's e to the negative t. And when I see this e to the minus 2s, what does that tell me? It tells me shift. So whenever I see this, this says it was a shift by 2. And I just want to remember that. So that I say, okay, my answer is 4 e to the 2t plus 2 e to the minus t minus, and now I'm going to have my functions, but I see that they're shifted by 2. So it'll be 3 e to the 2 times, what goes next? T minus 2, right? So shift by 2 really says that t is going to become t minus 2. Then minus 3 e to the minus t minus 2. And then finally, our on-off switch u of t minus 2. Oh, it just barely fit. Okay. We'll pretend like that fit. And we're done. All right. Good. Good. So just the moral here is I want you to remember this fact. Partial fractions only works for polynomial over polynomial. So if you ever see exponentials involved, put it off to the side. That's not in your partial fractions decomposition. You have to work with the pieces that look like polynomial over polynomial. Okay. Any questions? All right. Well, now that means we're ready for today. Today's the day. We finish our chart. And the last piece of our chart is this little tiny thing. It's called the delta function. And say, okay, what is it? Well, it's a function where the Laplace of the delta function is e to the minus as. And you're like, ooh, e to the minus as. We've seen that before. Where has e to the minus as shown up? Yeah, just like right above it, right? It shows up like in shifts. It's like, okay, so this has something to do with like something happens at time equals a, and there's like almost like a shift happening. Well, that's actually not too far off. So what is the delta function? Well, it's a little strange. So let me just sort of try to tell you the basic idea. The basic idea is it's a function that does something like that. It's just a whack the system. It doesn't sustain anything. It's just an instantaneous boom. So it can be things like if you're, there's an analogy, you hit the bat, you hit the ball with the bat. That's an example. Or maybe if you're thinking about springs, you have a spring and you whack it with a hammer. So it's just, you're giving this momentary pulse. And that delta function is just saying, okay, just something happened in that instant. But it's not sustained. It's just this one instantaneous boom to your system. So how does this work? Well, essentially the idea is it says, we're going to put everything on a single point. So delta of t minus a says, you're basically 0 except at this time a where we're going to think of infinity. It's kind of not right, but that's how we'll think of it. And what else do we have? Well, if we integrate from minus infinity to infinity, we get 1. So the right way to think about this is just to say, look, I just care about what happens at that moment, at time t equals a. And you'll see there's even a comment here that it's not a traditional function. It's kind of a weird function. But it's just trying to say, let's think about as though something is happening at time delta. Sorry, at time a. Now, you might say, okay, are mathematicians happy with this? Well, I'll tell you, if you look in the book, it'll say that, engineers used it for decades and they loved it because they kept getting the right answers. And annoyed mathematicians. Mathematicians get annoyed when people get the right answers but don't justify things. And so after a few decades, the mathematicians got involved and said, aha, we figured it out. And so there's this sort of generalized idea of what functions are. But the only thing that we need to remember is just this very simple rule about the delta function. Now, it comes off of here, which is to say the only thing that matters is what happens at time a. So if I integrate from minus infinity to infinity of any function, delta t minus a, well, I just say what's happening at time a. So it's f of a. So if I want to take the Laplace transform of the delta function, and I can even throw in anything I want, f of t. Well, we go to our definition, and this says, hey, since I have the delta function, the only thing that matters is what happens at time a. So you plug in t equals a into the rest of it. That's where you get the e to the minus as, and you get your f of a. All right, so that's the moral. It's basically a pulse. So, as a quick example, and this should be relatively quick, suppose we ask the following: what's the Laplace transform of t u of t minus 2 plus t delta t minus 3, just sort of to compare and contrast? Well, we can break it up into two pieces, t u t minus 2 plus Laplace t delta t minus 3. Now, are we ready to do the first part? Is this ready for us to go? Why not? Yeah, we're not in terms of t minus 2 yet. Darn it. Well, that's okay. That's easy for us to fix. We think of this as t minus 2 plus 2. U of t minus 2. Okay. Now is the first part ready for us? Yes. How about the second part? Are we ready to go? Yeah. You don't even have to do anything. In fact, this t right here, complete red herring. It's making you think something complicated is going to have to be done. It's like, nope, don't even have to worry about it. It could be a really crazy exotic function that we had no chance of finding the Laplace transform by itself. Okay, so for this part, we say, okay, so normally, if I think of just the function t, Laplace of t, do we know what that is? Yeah, it's 1 over s squared. Laplace of 2? Well, it's really 2 times the Laplace of 1. 1 over s. And then, of course, u of t minus 2 tells us what? E to the negative 2s. Okay, that's the first part. Plus, here, what do we have? Well, we see the delta function. It's e to the minus as. And then we just say, what's the coefficient? So the way we figure that out is, what happens at time equals 3? Plug in 3, what do you get? You get 3. So plug in 3 for t, and, well, when t equals 3, then t is 3. And now, Yeah, we're done. That's it. So it's actually super easy to take the Laplace transform of the delta function. It's going the other direction, of course. It'll be a little bit more interesting. All right. Well, I've not been very good about giving you a problem at the halfway point, and I see that we're at the halfway point in the class. So I'm going to give you a problem. Yes? Oh, you're right. You're right. I put e to the minus as. Thank you. Okay, so a problem. Given x double prime minus 2x prime plus x is delta t minus 1 plus delta t minus 2, x of 0 equals 0, x prime of 0 equals 1. Find the value for x of 3. So you have this second order differential equation. It's modeling something, but you start out at time 0. The system gets hit with a pulse at time 1. It gets hit with a second pulse at time 2. The question is, what happens when we hit 3? What's the first thing we should do on this type of problem? Laplace transform. Okay, so I got kind of carried away. I almost wrote Laplace again, so that's why my delta looks so bad. But okay, Laplace transform everything. Yes? That seems reasonable. And so Laplace transform of x double prime, you get s squared x minus 0s because of our initial condition, minus 1 initial condition, minus 2 sx minus 0 initial condition, plus x. Deltas are easy to take Laplace transforms of. So you get e to the minus s, e to the minus 2s. Okay, what comes next? Yeah, solve for x. So we group the x terms together. There is an s squared, a minus 2s, and a 1. And then the minus 1 comes across, so you have a 1 plus e to the minus s plus e to the minus 2s. And actually, s squared minus 2s plus 1 is pretty nice. It factors. S minus 1 squared. So you divide. So there is the answer for x, capital X, the Laplace transform of what we want. Well, now what do we need to do? Do our inverse Laplace. Now, the way I like to do things, especially when I see shifts, is I just think about what's happening with my parts. So 1 over s minus 1 squared. Now, this is not directly in the formula sheet. You have to combine pieces of information. So 1 over s minus 1 squared, how do we get that from our formula sheet? You have to combine two things. What's being combined? T to the n with n equals 1. So it's t. And the other thing you have to throw in is there's a shift. So if you see s minus something on the inside, that means that the transform came from multiplying by an exponential function. In this case, because we have s minus 1, it means we multiplied by e to the t. So 1 over s minus 1 squared is e to the t times t. Now that's true for each one of these. But when we have an exponential in s, not in t, but in s, that tells us shifts. So e to the minus s tells us shift by 1. E to the minus 2s tells us shift by 2. So what's the function for x of t? Well, t e to the t, there's no shift. Here, when we shift by 1, that means t becomes t minus 1. So t minus 1, e to the t minus 1, our on-off unit step function, t minus 1. Shift by 2, t minus 2, e to the t minus 2, our unit step function, t minus 2. Are we done? No. What's left? Plug in 3. So we plug in t equals 3. Well, when we plug in 3, the switches will both be on. So we'll get 3 e to the 3, 2 e to the 2, 1 e to the 1. So our answer is 3e cubed plus 2e squared plus e. Now, one thing that we can just sort of say, oh, it kind of makes sense. about one thing that's happening here. Notice that we have these pulses happening at time 1 and time 2. And what do you see in our answer? Well, we have on-off switches happening at time 1 and time 2. That's actually somewhat consistent. It just says something happened at time 1. Our system got a jolt. And that should affect what happens after time 1. And similar, something happened at time 2, so there's something that has an effect after time 2. So whenever we see these deltas in our problems, they're going to become used in our answers. It's just saying something happens, and we take that into account. All right. Well, any questions? Okay. Let's do another one. Group problem. We'll do it all together. I'm with you. A large group of people march at a regular pace when crossing a bridge. Now, the vibration of the bridge can be modeled by the following equation. Now, this actually happens, by the way, if you walk on a bridge, and especially if it's a small bridge, you can sometimes feel the bridge hopping, sort of pushing back a little bit, kind of like a mini trampoline. So it's kind of like a spring. So it's like, it's like a spring equation. Y double prime plus 9y. And then we have this infinite sum. Sum k equals 1 to infinity. Delta t minus 2 pi k. Now what's that? Well, what you should think of is at regular intervals, there's a push. It's like you stomp on that bridge. So you're giving the bridge a pulse of energy. And it's regular pace, that's why it's equally spaced. And if you look at armies, that's they march at a very regular pace. Dun, dun, dun. So this is actually where the inspiration for this problem comes from. Okay, so what is y? It's the vertical displacement, and it says solve the initial value problem using the method of Laplace transform. And of course, we look at this and say, well, we have to use the method of Laplace transform because we don't know how to handle delta if it's not method of Laplace transform. So no big surprises. Okay, so we begin. What do we do? Yeah, you take the Laplace of everything, right? We know this game. We've played this game before. Okay, so the Laplace y double prime plus 9y is going to be the Laplace of this really intimidating infinite sum. But hopefully it will become less intimidating in a few minutes. Okay, so we take the Laplace of both sides. Let's start with the left-hand side. All right, well, here, of course, you can break things up because it's really addition. What is the Laplace of y double prime in our case? S squared y, right? Because the initial conditions are 0. So s squared y plus 9, what's the next part? Well, I'm asking the question because we need it to, you meant y I know what you meant. Okay, all right. Oh, how embarrassing. Okay, all right. There we go. Okay, so s squared y plus 9y, we're good to go. Now this other side, what can we do here? Well, the sum is a sum. And Laplace works great with sum, so we just move it in. So just take the Laplace of each of these pulses. So what does this become? Well, it's the sum, k equals 1 to infinity, of e to the negative 2 pi k s. Okay. All right. So we've taken our Laplace transform. What do we need to do next? Solve for y. Now it's not too bad, right? Because I can pull out an s squared plus 9. And then I can divide by s squared plus 9. So we get that y, capital, is the sum. K equals 1 to infinity. And I'll write this as 1 over s squared plus 9 e to the minus 2 pi ks. Are we ready to take Laplace transforms? Inverse Laplace transforms. Yeah, we're basically just about right there. There's maybe one small tweak we'd like to do. 1 over s squared plus 9. We jump to our table. 1 over s squared plus 9. Does it look familiar? It looks really like sine. Good. So what would we, since we have s squared plus 9, what would we like upstairs? A 3. So we say, okay, no problem. We put a 3. You might say, that's the problem, Steve. You just changed the problem. Well, we compensate. We can put a 1/3 in front. We can even put it outside the sum. But now we're ready to go. All right, let's talk about what happens. 3 over s squared plus 9, we just looked at our table. That becomes sine 3t. But this e to the minus 2 pi ks, what is that going to do? What is that telling us to do? What the shift? Oh, wait, no. Shift by 2 pi k. All right. Yes? Okay. So, when we write y of t, this will be the sum. We're just going to take each piece. 1 to infinity. We have a 1/3 sine of 3 times, what comes next? T minus 2 pi k. Good. And then u of t minus 2 pi k. All right. Now, a question. Is there another way to write this function? Probably. Good answer. Okay. What's a better way to write this function? Yeah, you can multiply out sine of 3t minus 6 pi k. But if I shift by 6 pi k, what does that do to the sine function? Nothing. So what is it really? It's really sine of 3t. And notice, if it's sine of 3t, it's not depending on k. So you could even pull it out in front. So this is 1/3 sine of 3t times the sum k equals 1 to infinity u of t minus 2 pi k. So this is another way to write this function. All right. Now at this point you're like, okay, great, we got something. But actually, what does it mean? So let's think about what happens over the first interval. From 0 to 2, from time 0 to 1, what's the function? Oh, sorry, I should say from 0 to, I guess, 2 pi. From 0 to 2 pi, we are 0. Nothing's happened to the bridge. So the bridge is level. Okay, so initially, our bridge is on the level. Now, from 2 pi to 4 pi, what's it going to do? It's going to wiggle a little bit. It's going to behave like sine of 3t. Okay, so it goes up and down. It actually will go up and down 3 pulses. From 4 pi to 6 pi, what's going to happen? How many switches will you have turned on? 2 switches will have turned on. So you're going to actually be taller. What's going to happen in the next interval of 2 pi? A 3rd switch turns on. It gets bigger. And then what's going to happen? I like the answer. Someone knows where this is going. What happens is these are going to keep building and building and building. It's resonance. And the bridge is going to be vibrating higher and higher until you reach a point where the bridge cannot actually keep up. And it breaks. This has happened. Historically, this has happened. Which is why when you have armies training how to march, when they might march in cadence, but they get to a bridge and they're like, yep, they're all casual, because they know they don't want the bridge to break. They reach the end of the bridge, back in form, and they're marching together. It's because of this. Because they know that if you have everybody pulsing at the same time, you can feed in, it can actually cause the bridge to fail. So that's what's going on here. Math, saving lives for thousands of years, and bridges, I guess.